Welcome to Section 2, Implementing Variant Pattern Matching. In this section, we're going to take a look at the problem with std_visit, match syntax, implementing match from scratch, and future improvements and considerations. The problem with std_visit. In this video, we're going to take a look at pattern matching and the reasons why std_visit is not good enough. Pattern matching is a common feature of functional programming languages. It's a form of dispatch that looks at the shape of a given value and allows you to destructure its shape and perform an action depending on it. We can pattern match on std variance alternatives. As an example, imagine having a variant v of int, float, and char. When we use the match function and provide a lambda for int, a lambda for float, and lambda for char, what's going to happen is that we're going to destructure the variant, figure out the active alternative inside it, and then call the corresponding function. std_visit has a lot of problems. Firstly, it's inherently verbose and cumbersome. This discourages pattern matching on variants, even though it's a powerful and useful pattern. Visitation can be done through a struct with multiple operator call overloads, or through a generic lambda with an if const expr else if const expr chain. Both harm readability and increase boilerplate. Here's a comparison. Imagine that we want to visit this variant, and we're going to try out all the methods I described before. Firstly, with std_visit, you have to create a struct, such as this one, which provides 3 different operator overloads and 3 different actions. As you can see, most of the code here is boilerplate. If you want to use a generic lambda, you get the advantage of having the logic local to the visitation side, but there's even more boilerplate than before, and you need to use this kind of weird if const expr chain that distracts you from the real action. If we instead use the match function that we're going to implement in this section, you can see how the boilerplate is minimal, the result is short and readable, and how this function call resembles pattern matching. This is the syntax that will be provided by match. Firstly, as you can see, it's not just a single function call, but it's 2 function invocations one after each other. The first one takes a bunch of branches, which must be an exhaustive set of function objects that can be invoked with all the combination of the variance alternatives. And the second invocation is the one that takes all the variants used for the visitation and will actually perform the dispatch. An advantage of using a double invocation syntax is that it allows reuse of the generated visitor. Imagine that you want to use the same match visitor with multiple different variants in multiple different call sites. What you can do is bind the visitor generated by the first call to some variable, in this case vis0, and then you can reuse that with multiple variants later on. As we've seen previously, match can also be used with multiple variants. In this case, the set of lambdas must be exhaustive for every combination of the variance alternatives. And in the second invocation, you can pass multiple variants at once. This will perform the correct multiple dispatch. Finally, match can also return values. This requires all the branches passed with the first invocation to have the same return type. As you can see in this example, imagine having a variant of int, float, and char, and we want to return the string that corresponds to the type stored inside the variant. What we can do is simply invoke match, where every branch of the first invocation returns a string, and then pass the variant as a second invocation. What we'll get is a string that's returned from the correct branch, which can be then stored in a variable such as str here.